Lecture 7 Part B, Energetic for Work. In this lecture, we'll discuss plots of energy, work, and how work relates to changes of energy, and power. You already know that lifting an object above your head is harder to do than lifting that same object up an incline, and the more gradual the incline, the less force is needed. If I lift that same object up the more gradual incline to exactly the same height, it's the same amount of work, the same W, increasing the potential energy or the gravitational energy. That's a positive work or an input of energy, increasing the energy, the gravitational energy. So both boxes got lifted to the same height from the same starting position, the same Y initial to the same Y final. If the boxes weigh the same, the value of mgy is the same. So the same work is involved. If the incline is even more gradual, and I lift the same box from the same starting position to the same final height, then the same work is done in all three cases. But you know something is different, and that is it's easier to lift the last box up the more gradual slope. Less force is needed, but the same amount of energy has been increased for the box, the same change of energy or the same work. If you lift an object up a mountain, you change the potential energy. A force is needed to change the potential energy. How much force is needed depends on the slope of the mountain and the mass of the object. Let's say we have a ball, and the ball is going to roll down one of the four ramps. The steeper the ramp, the greater the force that's taking the ball down the ramp, the greater the force of gravity. But the change of energy for the ball is the same in all four cases. The ball will roll down these ramps. If there's no friction, the ball will reach the bottom with the same speed. In all cases, the change of energy, the loss of gravitational energy, is the same for all four balls if they start from the same height and end at the same height. But the slopes are different. The balls will reach the bottom with the same speed, but at different times. The force of gravity is greatest for the ball on the left of the steep ramp, and the force of gravity is almost zero for the ramp that's almost horizontal. The force depends on the slope, and the slope is the change in potential energy divided by the displacement, or the length of the slope. For a spring, things are a bit different, but the concept is still the same. The parabolic curve here is the potential energy of the spring, away from equilibrium. We set the equilibrium length to be where the potential energy of the spring is zero. The energy of the spring increases away from the equilibrium, both the positive displacements and the negative displacements. Whether it's increasing or whether it's a stretch or a compression of the spring increases its energy in the same fashion. As the spring, as you compress a spring and pull a spring, it gets harder and harder. There's greater forces involved. That's what's being shown in this graph. The forces are the arrows, the vectors are force vectors. The force vectors are greater for greater displacements, both positive and negative, away from equilibrium. The force relates to the change in the potential energy per the displacement, just as before. The change in potential energy per displacement is the slope of the energy graph. Where the slope is greater, the force is greater. The steeper the slope, the greater the force. Forces from potential always point in the direction that lowers potential energy. That is the negative, and the force is the negative of the slope of energy versus displacement. It forces the object, the particle, to go in the direction of lower energy. The force of gravity forced the ball down the ramp in the previous example. The force of the spring forces the mass to go back to equilibrium, where the energy is lower. It is forced to always go to equilibrium or to restore itself when it's stretched or compressed. Looking at this graph here of energy potential versus displacement, we see the energy varies throughout the displacement. Where the energy is dropping or decreasing, the slope is negative, but the force is positive. The force is the negative of the slope of energy versus position. Greater changes in energy, greater slopes, or greater forces. From x1 to x2, the energy is decreasing in the direction of x2. The force is pointing in the direction of x2. Where the slope is 0, the force is 0. Where the slope is 0, we say it's a location of equilibrium. We see there's 3 locations where the slope is 0 or the force is 0, at x2, x3, and x5. But at x2, a perturbation around x2, we return the particle back to x2. It's a stable equilibrium. To the left of x2, the force is positive. To the right of x2, the force is negative. The forces are returning the particle back to x2, back to the equilibrium, a stable equilibrium. At x3, the slope is also 0, the force is 0. But to the right or to the left of x3, the energy decreases. The force is pointing away from x3, whether it's to the left or to the right of x3, the particle will leave x3. It won't return. It is forced away from x3, whether it's the left or the right. That is an unstable location that is an unstable equilibrium. Here we see 4 frames of a particle on its way up. The particle has kinetic energy that is being lost from frame 1 to frame 2 and entirely gone in frame 3. Its speed or its kinetic energy is gone. Beneath the pictures of the ball moving up or losing kinetic energy, we see plotted TE, total energy, and potential energy. As the ball rises, its potential energy increases. When its potential energy is the same as the total energy, the kinetic energy must be 0, since the total energy is potential energy plus kinetic energy. This is the turning point of the object. It has no more kinetic energy, hence it's at the top. It can't keep on going. All its energy is now potential. So the object is forced back down the potential energy slope, forced back down, or to fall down. And the kinetic energy grows and grows as the object falls and loses potential. Thus, where the potential energy crosses the total energy is known as a turning point. Here we have a curve of changing energy with position, where TE, the total energy, crosses the potential energy, is the turning point of a particle. The particle starts from rest, where the total energy crosses the potential energy at x1. And the particle, in a sense, goes down the energy slope. It is forced down the energy slope to the stable equilibrium point of x2. As it's going from x1 to x2, it's losing potential energy, the values of those curves. As it decreases from x1, as the energy decreases from x1 to x2, the kinetic energy grows in proportion. The difference between the total energy and the potential energy is the amount of kinetic energy. The particle is moving faster at x2, and then as it moves from x2 to x3, it increases potential and decreases kinetic. Past x3, the particle is decreasing potential and increasing kinetic again. Where the potential energy is the least, the kinetic energy must be greatest. That's at point 4. From x4 to x5, the particle is losing its kinetic energy and increasing its potential energy until all its kinetic energy is gone, when the potential is a maximum equal to the total energy. With no kinetic energy, the particle stops and is forced back down the energy slope to repeat its motion. Thus, again, the turning points are where the total energy crosses the potential energy line. The difference between the total energy and the potential energy is the kinetic energy. By definition, kinetic energy plus potential energy is total energy. So we look at the values of potential energy on our graph and subtract those from total energy to determine the kinetic energy. In summary, force is always in the direction that decreases potential energy. Objects are forced down the energy slope. As they are forced down the energy slope, they gain speed. The force is related to the slope. It is not the value of potential energy. It is the value of the change in potential energy divided by the displacement, with a negative sign pointing in the direction of decreasing energy. The steeper the potential energy versus displacement graph, the greater the slope, the greater the force. The actual value of potential energy is arbitrary. Recall where we choose the potential energy of 0 is an arbitrary location, but the change of potential energy are physical. Work. Work is a change of energy. The sign of work, positive work, is an increase of energy, an increase of a particle's energy or a system's energy. Positive work, or input of work, or an increase in energy, if a force is in the direction of motion. If a force is parallel to the velocity, then the object is increasing its kinetic energy. It's forced to gain speed. This is an input of energy or input of work, positive work. The system gains energy. In this case, the kinetic energy would be increasing. Negative work is an output, a loss of energy. If the force is opposite direction of the velocity, then work is less than 0 or negative. Then the object is losing energy. The kinetic energy is decreasing for this object. The kinetic energy is changed by the amount of force and how long, the distance, that force is applied. A force applied for a longer distance will have a greater input of energy or greater increase in the kinetic energy. Push a box harder, or for a longer distance, it will cause a greater change in kinetic energy. So the force times the distance is equal to the change in kinetic energy. If there's friction, then the force of a push versus the external frictional forces are doing battle. The greater amount of external force is our net force. When we talk about forces in work, we're talking about the average net force. So the remaining force between external forces will be what's changing the object's energy or kinetic energy. Or the push does positive work and the friction does negative work. The difference between the positive work from the push on the box or the object minus the work of friction is the total work on the object. A person lifts up a large amount of weight, he does work on the weight. He increases the gravitational energy, the potential energy of the weight, depending on the mass and how high he lifts it. The prisoner pushing on the wall, does he do work to the wall? Well, if the wall doesn't get displaced, then the forces on the wall haven't created any displacement. The wall doesn't change its energy. If the wall doesn't get lifted up or sent down or move to change its speed, or doesn't get compressed like a spring, or any chemical reactions, explosions, or nuclear explosions, then the wall has no work done to it. The wall didn't change any energy. So if there's no displacement, despite this man's forces on the wall, if there's no displacement, there is no work. There is no external work from the man. He's certainly losing energy as he keeps on pushing on this wall. There's internal work. The man loses energy. There's a negative work from the man, from the prisoner, and that's from his body flowing, his heart beating, his blood moving around, his muscles moving. Those are all internal forces, internal work that's being lost from him. But there's no external work on the wall. The wall is not changing its energy. That force on the wall is not creating any displacement of the wall. His work is all lost to environment. None of it went to the wall. The precise connection between a force and work is the integral, or the sum, of the forces in the direction of the displacement. Graphically, if we did force versus displacement, work is organized energy, increasing a particle's kinetic energy, in lifting an object up, compressing a spring, but not just increasing random motion like thermal energy. Work is a change in a system's energy, but a change in its system's energy, so it moves faster, gets lifted higher, springs compress, organized energy. On a force versus displacement graph, work would be the area under the curve. Power is the rate of change of energy per time. The rate of or time it takes for energy transferred into a system. The man lifts up the weight, does work on the weight by lifting up those masses, but the faster he does it, the more powerful he is. The same amount of work of lifting that same weight, the same distance, can have different powers. If somebody lifts that same weight, the same height, but does it faster, he's more powerful. So power is change of energy or work done divided by a time interval. And the units of energy are joules. So joules per time or joules per second is the unit for power. Watts, named after James Watt, the 18th century steam engine. Units of energy are joules, which is force times distance or newtons times meter. 1 joule is the work to lift an apple 1 meter. So something on the order of joules is in the order of lifting light objects about a meter. Tens of joules would be lifting something that's around equivalent of 10 apples, the weight of your textbook, about a meter. 1 kilojoule or 1,000 joules would be the work, the change of energy of lifting heavy weights, about a meter. A megajoule, or thousands of kilojoules, or millions of joules, are energy transfers converted from a kilogram of gasoline. So when you have homework problems that are in joules, if your answers end up in joules or fractions of joules, it's the work of lifting light things. Tens of joules, the work of lifting ordinary things. Thousands of joules, the work of lifting heavy things, all about an ordinary distance of a meter or so.